In the name of God, the compassionate, the merciful, Engineering Plasticity, Chapter 3, Yield Criteria, Part 13. Continuing with our quadratic Hill yield criteria for the anisotropic yield criteria, we are going to examine the plane stress case. Okay, so here I have given the general equations for the three-dimensional case, which we derived before in the previous part. We are going to use these for the plane stress case. Okay, that's the yield function, and these are the derivatives of plastic strain relative to lambda, which is equal to the partial differentiation of yield function relative to sigma 1, sigma 2, and sigma 3, which we obtained before. Now, for plane stress, obviously, sigma 3 is 0. So if in these equations we just put sigma 3 is 0, we get here 2g plus h, sigma 1 minus 2h, sigma 2 for partial derivative of yield function relative to sigma 1. Similarly, for partial differentiation of yield function relative to sigma 2, simply we put sigma 3 here equal to 0. So we get 2f plus h sigma 2 minus 2 h sigma 1, and similarly for the third one we get this one. Okay, since here we have sigma 3 is equal to 0, so all of this minus sign we have here. Okay, and from here these are the ones. Therefore, for this equation, if we obtain R0 value and R90 value, it is the R value in the direction of rolling, and this is the R90 is the R value in the direction perpendicular to the rolling. Okay, so in order to do that, we have to get this, the ratio of the in-plane and out-of-plane plastic strains under uniaxial stress sigma 1 for R0, and for R90 the plastic strain ratio under uniaxial stress sigma 2. So for the first one, R0, we have the epsilon 2 over the epsilon 3 in here. Okay, this one over that one, of course sigma 2 and sigma 3 are 0. So sigma 2 is here 0. We have put sigma 3 before equal to 0. So we get minus 2h sigma 1, and here sigma 2 is 0. So we get minus 2g sigma 1. So that one over this one we get h over g. And for the second one, R90 under uniaxial stress sigma 2, we have the epsilon 1 over the epsilon 3. Okay, that one over that one. So here sigma 1 is 0, so we get minus 2h sigma 2, and here we get minus 2f sigma 2. So we get h over f. Okay, and then from here we can use h is equal to r0g, and we knew that sigma 3 is 0 because it's plane stress. The yield condition then can be written as this yield condition, sigma 3 is 0. Now we have here f sigma 2, here we have g sigma 1 because sigma 3 is 0, and here we have h sigma 1 minus sigma 2 over to the power of 2 and minus 1. So instead of h we substitute r0g, we get this one, and which in turn may be expressed as this one could be expressed as this. Here we have brought sigma 1, we got 1 sigma 1 square here, and we got 1 sigma 1 square here. So sigma 1 square times r0 plus 1 times g. So g times 1 plus r0 comes in the denominator, and for sigma 2 we have f sigma 2 squared, and here we got r0 sigma 2 squared positive. So we get f plus r0 times g, and because we got a g r0 here, so r0 g times sigma 2 squared and f times sigma 2 squared, so we get this on the numerator. And for 2 sigma 1 sigma 2 with negative sign, we have it here. So we have here r0 g divided by g times 1 plus r0. We get this g cancels out, and we get this, and then we have 1 over 1 plus r0 g. Okay, so that this equation becomes like that. So that is our yield criteria for the plane stress. Still we have f and g to find out. So we are going to find this out. Now these equations were again obtained from previous slides. In previous slides, in the previous part, we had sigma 1, 1, 2, 2, and 3, 3. Here we have these principal stresses, so I just changed this to sigma 1, sigma 2, and sigma 3. So here again sigma 3 is 0. So and we have this equation r0 equal to that h over g, so that we could write down here h divided by g is equal to that over that. Okay, so if that divided by that gives us this expression, and here r90 is equal to h over f, so using r90 h over f, we get this. Okay, you have to do some manipulation to get this relationship by dividing this by that and this by that. Okay, you can do that. Okay, so if we get these relations, then these are the relations we got from previous slide. Then we could solve these two equations together to get sigma 3y and sigma 2y. So in here, solving for we obtained these two equations from previous slide. In here we solve for 1 over sigma 2y to the power of 2 and 1 over sigma 3y to the power of 2 using these two equations. Okay, we can obtain these two in terms of sigma 1y. So we get here 1 over sigma 2y because we have two equations, two unknowns. These are two unknowns, and supposing these two are knowns. Obviously all three of these are knowns, but I mean we are using two equations to get these two in terms of this one. So after some manipulation we get this. Okay, so this is 1 over sigma 2y to the power of 2 is equal to this term. So we find out sigma 2 in terms of sigma 1. That's yield strength in direction 2, yield strength in direction 1. And similarly, yield strength in direction 3, we find out in terms of yield strength in direction 1, and using these parameters. Right. Therefore, substituting for sigma 2y and sigma 3y in these three equations which we had obtained before, we get f and g in terms of sigma 1y, r0 and r90. So that's what we get for f and g. And then using these values we obtain these relationships. Okay, you can see here that we can get here sigma 1 y to the power of 2 is equal to 1 over in fact 1 over this is equal to 1 plus r0 times g. So if we reverse that, we get sigma 1 y squared is equal to 1 over g times 1 plus r0, and then from here, if we substitute for sigma 1 y squared into this, or perhaps substitute this into that, doesn't make any difference, we get a relationship between f and g like that. Okay, so these two relations we can use in this equation that we obtained before. You remember we obtained this before in terms of f and g, and therefore here we got this g and f, and we can substitute here. For instance, if you look here, f plus r0 g times 1 plus r0 is this one, and 1 over g times 1 plus r0 is this one. So this capital R and small r the same here. Some books use capital R, some books use small r, but I should have used the small r throughout, but I had forgotten. So this is the same thing. I will change it in the PowerPoint and upload it for you. Then from this relationship we obtain this by substituting the sigma 1 y squared for this one and this one for that one. So we get sigma 1 squared plus that relationship sigma 2 squared, sigma 1 2 and sigma 1 y squared. So you can see here that we have obtained this relationship for quadratic Hill criterion for anisotropic materials for plane stress. So that is the plane stress anisotropy. Okay, so we don't have any sigma 3, only we have sigma 1 and 2, and that's the Yale criteria we are going to use. Now in 1993, Hill again proposed another Yale criteria for plane stress problems with planar anisotropy, and this criteria has the form like this. As you can see, again we have sigma 1 and sigma 2 in here. Also we have P, Q and C, and these are the constants. For instance, C is this constant according to that, and P is this constant, and Q is this constant. So let me just okay, so that is one, the other one, this one, and so sigma 1 and sigma 2 are the stresses, and this sigma 90, sigma 0, etc. are the stresses or yield stresses in the direction of rolling, perpendicular to the direction of rolling, and this sigma b is the biaxial stress. That means that if you do a biaxial test and you get the sigma b for the biaxial test, you put it here. Okay. So that's all I want to say about the anisotropic yield criteria. I think it's quite enough, and we will see what we can do in the next part.